nested interval theorem. So, to motivate this question, how would a blind pediatrician, a doctor, measure the height of his patient child? That's the question, and here is how he might solve it if he were German. Okay? So what you do is this, you know, probably the child is not this high. So what I do, I raise my hand somewhere halfway and slap. And if I hear a scream, then I know what? Then I know I need to go higher, right? So what do I do? This is what this is showing. Understand? Well, you see, I'm glad you still find this amusing, right? That's why. So. What have you observed by the first slap? So if there was a vocalization, let's say there was a vocalization, that means that that you see you know this elevation, and now and this was your lower estimate for the elevation. So now your approximation is already within 1/2 of what your original confidence interval used to be, right? So you thought the child is from here to here, right? So you gave a slap in here, in the middle. If there was a vocalization, you know his top part is in the upper part of the interval. If there was no vocalization, it's in the lower part of the interval, but regardless, your confidence interval has shrunk to 1/2. Then what you do next? What you do is you estimate between here and here. You slap. If you hear no sound, then he is in here. Okay, so what we have is we have the first elevation is your, let's call it I1 or I don't know, maybe I0. That's your first estimation. It was a closed interval, right? Next estimation would be what? Next estimation would be this, right? Next estimation is that the length is contained in I1. And then the next is that it's contained in I2. Do you see this? Notice that my estimation for the exact altitude, the exact top of his head, is now between smaller and smaller two numbers. Sorry, they're not smaller, but the distance between the upper bound for my estimation and the lower bound for my estimation is shrinking each time by a factor of 2. Do you see this? So I can say that, like, if I take this procedure, if this doctor will be this pediatrician will use this procedure, then you can see that the length. So you can see that the following. Why is it called nested interval theorem? Well, you have I0 contains within itself the interval I1, and I1 will contain the interval I2, and etc. The next will be contained onward. So that's why it's called nested interval theorem. And observe that in the way I describe this procedure, the length of the interval I sub n will be equal to 1/2 the length of the interval I sub n minus 1. You see that it's basically the interval is like a measurement of the distance between my upper bound and my lower bound for my estimation, and my upper bound, lower bound at each new step, the distance between them decreases by 2. Okay? And from the original, it's 1/2 to the end. So the measurement is growing to 0 very fast. There are not going to be many slaps necessary, so it seems, to measure the precise height of the child. But in this, so why did I think of it? Because when I read this thing, I remembered how I dislike children so enormously, right? And in fact, I had to deal with them, you know, when I was teaching, well, when I was working in the aquarium, I talk about sharks, and they, oh, does it bite, Mommy, it's scary, right? And I would just leave me alone. Why did I work with sharks? And why did I work with horseshoe crab? Because I just wanted to be left alone, right? So they come to the penguins, and they scream, and they're so happy, right? And that annoyed the hell out of me, so I chose the animals they don't like the horseshoe crab. Here, water is very cold, do you want to touch it? No, get the hell out. And my days were easier. When I was younger, some women cared whether or not I like children. Now it doesn't bother them at all. That's the sad thing. There were people, oh my God, he doesn't like children. Oh my God, what a loss to the human race. Right. Good. So now let's try to understand this rigorously. What is this nested interval theorem like?
Convergence.
Well, we need to state a precise statement here, right? What is it that I drew here? What is precisely happening here? And this is going to be generalized later on, right? This is a tool that is very commonly used in many times in mathematics. You will recognize it. Hopefully, some years in the future, you would just read it. Ah, yeah. So here is that theorem. So it's called the nested interval theorem, and what it asserts is the following. So first theorem that I will mention, it's going to be something that I use to prove this nested interval theorem, and this claim is a monotone bounded sequence of real numbers converges in R. Okay? So do you understand what I mean by the word monotone? Monotone means increasing or decreasing or non-decreasing, all that stuff, right? Increasing could be the point just goes either higher or stays at the same level, but never lower. Okay? So, proof. So, let Xn, which is a subset of R, be monotone and bounded. So suppose we have x1 is less than or equal to x2, less than or equal to x3. So what I'm saying, it's increasing, right? So you see the next point is at least as high as x1, the next is at least as high as x2, so that's increasing, okay? So this sequence is remember what bounded means. Bounded means that that I can encapsulate the sequence inside of an open set. And of course, well, I can take the lower edge of the open set to be slightly less than x1, and the upper one, that's why I need bounded. It could potentially go up to infinity, but I'm claiming it doesn't go to infinity. So the entire sequence has, so if I take A to be xn, where n is bigger than or equal to 1, and then A is bounded above by, so I just bounded above, I want to say, it's bounded above in R. And that's according to hypothesis. What do you think the sequence converges to? Remember R. What does it converge to?
X1.
Sorry?
X1.
Well, it goes from x1 to x2, it climbs up.
Yeah,
so
but x1 is the smallest one.
Smallest, but what's the well, I'm asking about the upper bound. So in this case, bounded, I really only need to consider the upper bound.
The supremum.
The supremum. Right? So how do I know the sequence will converge? In R, because, well, it goes up, and there is going to be an upper bound. If there is an upper bound, there is the least upper bound, and that ends up being the convergent. Yes?
Xi for some I. I mean, eventually it will.
Well, notice that less than or equal means I have no idea. Maybe equal doesn't apply. All I'm saying is the sequence either stays at x1 or climbs, and stays at x2 or climbs. Basically, its only option is to go up. It could potentially go up like this. It could go up very fast. So it's bounded above in R. And we're going to set x to equal to the supremum of A, and that has to be the convergent. So then limit as n goes to infinity of xn must equal to x, and here is why. Because why? So what I do, how do you show that x is the limit? You take epsilon, and for any epsilon that I drop below x, all the members of the sequence except for finitely many are within that ball. So let epsilon be bigger than 0, so I'm going to draw it. So here is the situation, here is x. Here is x, here is x plus epsilon, and here is x minus epsilon. Okay? Now what happens? So this is the supremum. The sequence has to eventually, right? So the sequence, what does the sequence do? It climbs. It climbs to the least upper bound, right? So it climbs. That's what this means. Either it might stay a bunch of times on the same point, but it climbs, and eventually what? Eventually the sequence is already here. You see what I'm saying? So the sequence is within this interval, actually only within the lower part of the interval if you are precise. But what you can see is this. You can see that if you want to be precise, you can say x minus epsilon naught upper bound, which implies what? Which implies that x to the sub n is bigger than x minus epsilon for some n belonging to the natural numbers, which implies that if which implies this, I'll just write it like this. So I can write x sub capital N less than or equal to x sub capital N plus 1, less than or equal to x sub capital N plus 2, etc., less than or equal x. Okay? So, so you can see that eventually sequence, in ball of radius epsilon around x for any epsilon, which implies xn converges to x. That's what convergence is. Delete the first few terms, maybe the first many terms, but the tail of the sequence is within the ball. And that follows very simply from the increasing part, the increasing condition of the sequence. Decreasing will be exactly the same, but with the decreasing I take the what? Infimum, and I prove that the sequence converges to the infimum. This picture will suggest what happens, okay? In the infimum, it will be the upper part of this x, the upper part that contains all the points. So this point is established. The proof for decreasing sequence is the same, or just every decreasing sequence is minus times an increasing sequence. So you can always kind of play with this idea.
How do we choose that capital N in terms of epsilon?
I don't know. I don't know the sequence. I just know that a choice will be possible because x minus epsilon is not the upper bound. So some sequence eventually goes beyond it, but because it's increasing all the others, as soon as one is there, all the others go. So I do not know how to make the choice explicitly, but I just know it exists. But some people find it's that's one thing they don't like about analysis sometimes, and they cannot come to terms with it. They say that unless I specify a function that tells me how this choice is done, this is not a proof. It's not constructed. I didn't construct n of epsilon. But you see, I suppose in this case you believe that, well, you can just look at the argument, it seems right. It seems that there will be a choice. Good? So in my notes I also show what happens if it's decreasing. So you can say if xn is decreasing,
And it converges
the proof is similar. The argument is similar.
It's the supremum of the.
Right. You can either prove you just use the same proof. You translate a decreasing sequence into an increasing one and then conclude the same argument, or you construct an entirely new proof with the decreasing sequence. It's just as easy. Okay. The argument is similar. And do I have time to at least state the nested interval theorem? Okay, so I'll just state the nested interval theorem and then we'll go. So what it says is this: if we have a sequence in, so it's a sequence of closed, nested, and bounded intervals of R. In other words, what this means is I can see that I1 will contain I2, and I2 will contain I3, etc. That's nested means, right? So one interval is nested within the previous interval, and each of them is closed and bounded. You understand what it means? Closed and bounded is like in this picture. So it's from A, including A, to B, including B. Okay? So each IN is some interval from A sub n, B sub n. Yes? So that's IN. Such that, and another thing that's important, such that, so then, I can say this. So I can say then the intersection. Then, if I take the intersection of all those sets, this will not be empty. Furthermore, if the length of the intervals IN goes to 0, then the intersection contains precisely one point. Very important theorem, but for example, you use it in the proof of Goursot's theorem, and that is in complex analysis. If you take any closed triangular curve and you integrate around it by an analytic function, the answer will always be 0. Okay, and the proof follows one part of the proof follows from this idea. It's just nested set theorem is an extension. It's not enough to have an interval. It's true about any closed sets that are decreasing in size, and each contains the next set, provided the space is complete. Provided in that space every Cauchy is convergent. So that's all you need. Okay. Goodbye.
Will the reduction of the interval decrease by a constant factor?
It doesn't matter. What matters is it will contain only one point as long as the limit is 0. They might decrease at arbitrary rate. But if eventually it's squeezed to 0, it will be only containing one point.